we present our work on generating realistic training data from time-lapse imagery for reconstructing dynamic objects under occlusion. Occlusions are very common, but also very complex to handle. In this example, we've got a pedestrian in front of the first car, and there's also a car behind it. As we can see here, state-of-the-art methods only manage to reconstruct the car in front, both 2D and 3D. One of the key challenges is the lack of data annotations for occlusions. However, getting supervision for complete representation is hard because annotating the occluded parts are difficult, even for humans. Here, we highlight the limited number of annotations for complete segmentation. And this is just for 2D. Annotating 3D information under occlusion is even more challenging, further limiting the amount of available 3D annotations. Given time-lapse images from a stationary camera, our goal is to automatically generate pseudo-ground truth data with a realistic occlusion configuration. Here we show the composited RGB image as well as the pseudo-ground truth supervision data for key points, segmentation, and 3D shape and pose that come from off-the-shelf methods. We show that these data can be used to learn object reconstruction under occlusion, with a focus on two main classes of dynamic objects, vehicles and humans. To start off, we discuss how to automatically generate realistic supervision data. First, we observe that off-the-shelf methods work well on unoccluded objects for both 2D and 3D prediction tasks. Therefore, they can be used as pseudo-ground truth to learn object reconstruction under occlusion. Given a time-lapse video, we use an unoccluded object detector to identify unoccluded objects, here vehicle and human highlighted in yellow. Once unoccluded objects are identified, with the camera intrinsics and ground plane equation, we use off-the-shelf methods to get accurate 3D object pose and shape of these unoccluded objects. In this figure, we show the ground plane together with 3D reconstructed objects. Using the poses of unoccluded objects, we can geometrically compose them back into the background image in a clip art manner. In our approach, we randomly sample non-intersecting 3D objects and copy-paste them back into the background image at their original positions in order to preserve correct perspective, starting from the farthest to the closest. Observe that it can produce physically accurate and realistic occlusion configurations. Each clip art image comes with complete bounding boxes, segmentation masks, key points, and 3D poses and shapes referred to as pseudo-ground truth as these were predicted by off-the-shelf methods. Here we show another example of our 3D-based clip art data generation, where we composite multiple layers of occlusion of humans and vehicles. We can apply our method to any stationary camera with intrinsics and ground plane information, showing the scalability of our method. Next, we show a comparison between images composited using the 2D-based methods such as WALT, on the left, and our 3D-based method, on the right. Focusing on the green and red crops, it is easy to see that our 3D-based compositing method generates realistic and geometrically accurate occlusion configurations, in contrast to the 2D-based method, where cars and people overlapping in an unfeasible way. Similarly, for the second camera as well. Quantitatively, our analysis shows that training with our 3D-based compositing data significantly improves performance across all training data fractions, especially at low data regime, compared to training with 2D-based compositing data. This is because our 3D-based approach generates higher quality and physically accurate occlusion configurations with the same amount of training data, aligning more closely with the real-world distribution. Importantly, this data efficiency can allow us to scale to a larger number of scenes more efficiently. We also observe that the accuracy of segmentation and 3D keypoint estimation is much more robust with increasing occlusion percentage when they are trained using our 3D-based compositing data, showing significant improvement over 2D-based compositing or COCO dataset. Next, we show some qualitative results of the object reconstruction method that is trained on our 3D-based clip art dataset. Back to the image in the first slide, by training with our clip art data, we can observe accurate localization of key points and 3D poses of people and vehicles, especially the vehicle in the back. We show some additional results on a video sequence. Observe that the method is able to predict accurate segmentations, key points, and 3D reconstruction, specifically when objects occluded each other. Note that the result is computed per image here and no temporal information is propagated. Similarly, check out accurate reconstruction of the white car when it has multiple layers of occlusion. Observe that it is being reconstructed accurately even under severe occlusion. Similarly for people, our method is able to produce accurate 2D segmentation as well as 3D shape and pose, especially when the person colored in blue is being occluded. Our method is also able to perform well in a crowded scene, with accurate segmentation as well as shape and pose reconstruction. In conclusion, we introduce a novel method that automatically generates 2D and 3D supervision data from time-lapse imagery with realistic occlusion configurations without human labeling. We also demonstrate that using our generated data significantly enhances training efficiency and the accuracy of 2D and 3D object reconstruction on real-world data, particularly in scenarios with high occlusion. Thank you for listening, and please check out our website for more information.